Now let's look at an interesting kind of collision problem. It's really not a collision, you treat it like a collision. It's always in the collision section of the book, right? So usually you're talking about a person on a frictionless sled or a barge or something that's free to move. And the person has a significant mass, mp, and the barge, I'll call it a barge, has a significant mass, mb, and this is frictionless. And since it's frictionless, the person and the barge are isolated. They make an isolated system because there's nothing that can apply any force lateral because the surface is frictionless. We'll say the barge has length L from 0 to L, right? And we'll see if we can figure out what's going to happen when a person walks from the end to the center of the barge. So they're going to walk to L over 2. What's going to happen? So first let's test our intuition with the demo. So here is my frictionless barge. It's on wheels. I've bolted a couple of the carts together. Pretty frictionless. It's 0 to L long. And first I just want to test our intuition. What's it going to do when I walk on it? So let me push it over this way. And then I got to jump up here. All right, so I will be the person, and this is the barge. And I'm going to stand on the edge, and I'll walk a little more than halfway, just so you can really see the barge move. So as I walk forward, the barge moves backwards. Whoops, a little bit of friction there. So let's now calculate what we expected to happen. So we're going to calculate how far does the barge move back? That's really the question. All right, so to do that, we would hope to have sort of an initial and a final state. So allow me to erase my frictionless word here, because we can use this as our initial position of everything. So on the x-axis, I was at the origin, the edge of the barge is at the origin, the barge is L long. And what's going to happen is we're going to walk a little bit, and we just saw that the barge gets pushed back. I walked, let's say, to L over 2. Of course, the origin isn't here anymore. It moved back. So what we're trying to calculate is this, minus s, the shift backwards, where this is the origin. I'm at L over 2. So how much did it shift back? That's the question. All right, so the way you can think of this as a collision is the idea that I collided with a barge. We had an interaction with each other, yet our center of mass doesn't move because we are an isolated system. So all we got to do is calculate the center of mass before and the center of mass after and set them equal to each other, and that should tell us the answer. All right, so let's look at the initial x center of mass, right? So the center of mass is 1 over the total mass times the position of each mass times where it is, right? So 1 over mp plus mb, right, times my position times my mass, but I'm at 0, so that's nice. So that's m of the person times 0, plus now we got to do the barge. Well, if we assume its mass is uniformly distributed, we can think of it as a rod, and we know its center of mass is at the center, and we know as isolated object itself, it acts like all its mass is at the center. So this would be mb times L over 2. If we treat it as a point particle, it's at L over 2. That's the initial. Now let's look at the final, where everything is shifted around. Final center of mass. Where is it? Let's see how we want to write that. Again, it's 1 over the total. 1 over mp plus mb. And now it's my position times my mass times my position plus the center of the barge times its position. So my position is what? I walked forward, I walked to the middle, right? This distance is L over 2, but I'm not at L over 2. I'm at L over 2 minus s because it moved back. So it's mass of the person times L over 2 minus x. Minus s. That's how far I got. Okay. Plus the contribution of the barge. And let's see, the center of the barge is there. So it is also L over 2 minus s. Yes, I forgot. If I walk to the center, then our masses are at the same place. So mb times L over 2 minus s. Right, okay. I really should start reading these notes ahead of time. All right, so now what we're going to do is equate these two. Right, let's equate this equals to this. So the first thing we can do is cancel the common terms. So we would cancel that and that. Total mass doesn't matter. And then we would say, oh, well, that's 0. So we have mb times L over 2 equals mp times L over 2 minus s plus mb times L over 2 minus s. Right? And then, I don't know, we could see that probably the quickest thing to see is that mb L over 2 is over here and mb L over 2 is right there. So that one cancels, right, if we're doing our algebra tricks. And then we're down to just mp times L over 2 minus mp times s plus, or minus mb times s equals 0. So we could solve this. What are we solving for? We're solving for s. Okay, let's solve this for s. So we would say minus mp times s minus mb times s. So we would bring those over here, and it would be mp plus mb over here, and s over here. Yet we still have this one mp times L over 2, which we'll have to bring over here, minus mp. I've algebraed myself here. Okay, let's solve this now. Are we ready? We're solving this for s. Let's say this is equal to 0 is equal to mp times L over 2 plus mp plus mb times minus s. Let's do that and bring that over here and then divide and solve for s. Thank you. And what you get is mp over mp plus mb times L over 2. So that is how far it shifts. It depends on the ratios of our masses. And we can check this sort of with common sense. What if I weighed essentially nothing compared to the barge, right? If I weigh nothing compared to the barge, then what's going to happen? The barge isn't going to care that I walk to the middle. It's going to have very little effect. If it was me and like an aircraft carrier, the shift is going to be nothing. And sure enough, if I weigh nothing compared to the barge, this is basically 0. So the shift is essentially nothing. What if I weigh a lot more than the barge? What if it's me and a knee board? Somehow I can balance on a knee board and I were to walk, then the barge would respond a lot, right? The barge would really want to move back. And sure enough, if my mass is biggest, this is basically 1, almost 1. And in that case, yeah, the barge would move back to where I would pretty much stay in the same place. But the maximum you could ever get is L over 2, because I only walked to the point L over 2. So the answer makes sense.